All right, we are going to get into normal distributions today. This is, in my opinion, one of the cooler things that is true mathematically, and it lets you really analyze some data in kind of a cool way. So this whole section is obviously about normal distributions, and so anything that has normally distributed data, where most of the data is going to be clumped in the center, and then it kind of trails off in both directions. We've seen a lot of that since here. There's a scenario here, but before we get into any of the scenario, let me give you the what's called the empirical rule. So I'm just going to draw it down here in the bottom. And this is one of these things that these can be drawn a few different ways, but I'm going to show you the way that I kind of like it. So this is a thing called the empirical rule. And what it is it's a way to analyze any set of normal data. So let's say we have a normal curve. Okay. So data curve, bell-shaped, look a little something like this. If it's normal data, let's assume, let's say perfectly normal data, then located right in the center is going to be the mean. They sometimes will use the Greek letter mu for this as well, which kind of looks like a weird little U with an extra tail on it. But we'll see that kind of going forward. But anyway, mean is going to be located in the center. Now, from this, what we can do is based off standard deviations, which again, we reviewed in the warm-up. Standard deviation is average distance from the mean. The way normal distributions work is if you go out specific numbers of standard deviations from the mean. So let's just say we went out one standard deviation, and we'll say population standard deviations here. And same thing if we went one in this direction. So one to the left, one to the right. What's really cool about this is in a normal distribution, this is going to contain 68% of your data. Some people round it and call it 70, and it's called a rule of 70. Maybe you've heard of that before. But within one standard deviation of your data in each direction is going to be 68%. Or in other words, a little over 2/3 of your data always falls in that group for normally distributed data. If you go out an additional standard deviation, so let's say you go out 2 standard deviations in each direction, that will actually contain 95% of all people or all data that you survey. So most everything, everybody but 5% falls within 2 standard deviations of the mean. And if you happen to go out 3, so 3 standard deviations in each direction, that's going to actually contain 99.7% of all data. In other words, as you would expect with a normal distribution, most of the data is clumped near the mean. And then it gradually gets lower and lower and lower. And so nearly everything has to fall, 99.7% of the data falls within 3 standard deviations of the mean for normally distributed data. Now, there's a lot of ways you can also break this down. Here's what I like to think of on this is, remember, this is your midpoint. So you can also think of it as half of the data is below the mean and half of the data is above the mean. So these can each get broken up as well. So like if this is 68% of the data, well, you can think of it as there's 34% there and there's 34% there, just cutting it in half. And then also in the same regard, if this is 95%, we could take 95%, subtract the 68 from it, and then divide it in half. So these two parts, and I just like to write these down because these numbers kind of come up here and there. So 13.5% of the data falls in that range. That's just me taking 95, subtracting 68, and dividing it into these two sections. And then if we do the same thing right here, take 99.7, subtract 95, and divide it by 2, these are both 2.35%. Now, we don't always need all these percentages and all these numbers, but this is going to allow us to answer a bunch of different questions you're going to see today. So this percentage breakdown holds true for anything that we think is a normally distributed set of data. We can follow this to make predictions about how many people or how many data points are within each range of values. So we're going to reference back to this a ton. So you'll flip back to it here and there, and we'll use it. So let's read this first problem. So it says, there we go. An example of an early application was in the year 1817. A study of chest circumference. So they measured like around guys' chests, how many inches they were, among a group of Scottish men exhibited a normal approximately normal distribution. So telling you it's normal. It's going to follow this empirical rule. The chest circumferences ranged from 33 to 48 inches with a mean test measurement of 40, okay, and a standard deviation of 2. So in this case, we've got the mean is 40, the standard deviation is 2. Just to jot those down as we're reading this. Use the empirical rule to help you understand the distribution of chest circumferences in this study. So we can actually draw this same curve. And a lot of times this is an easy way to help you understand and answer these types of questions. So the mean is 40. Boom, 40. Standard deviation is 2. So if you go up 2 or if you go down 2, that's going to be the first standard deviation. Sorry, now you can see that better. My bad. So basically, we know that by standard deviations, this is going to go up and down by 2s. So we can add the other ones in here. This would be at 44. This would be at 46. So that's 2 standard deviations out and 3 standard deviations out. Same thing in this direction. That'd be 36 at 2 standard deviations and 34 at 3 standard deviations. And actually, this makes complete sense with what they said in the problem. We said 3 standard deviations out is from 34 to 46. They said they actually did get people from 33 to 48. That accounts for that very small percentile of people outside of this 3 standard deviation range. Okay, so what's this question say? What range of chest measurements contains 68% which fall closest to the mean? So before you look at this empirical rule, you're probably like, well, that's a really random number for them to ask about. But it's actually not. It's 68% because 68% fall within 1 standard deviation of the mean. So in our case, that'd be everybody from 38 to 42 inches. And that would be the answer to that question. You're giving the range of values that meet a certain percentage, whatever. So this part can vary. They can give you all kinds of weird percentages. They could say things like 95%. What's the 95% closest to the mean? Well, that's 2 standard deviations out. So that'd be 36 to 44. If they said 99.7%, you'd be like, oh, that's 3 standard deviations out. That's 34 to 46. And so they're going to ask a lot of questions. You're going to see this in the assignment stuff today, where you don't necessarily always need to draw this out, but it can be helpful, especially as you're doing it early on, to be able to help you answer these questions. And there's a follow-up one here. It says, what would you expect the chest measurements to be for the 2.5% of men with the smallest chest measurement in the population? And you might look at that again and you'll be like, well, that's weird. 2.5 wasn't any of the numbers that we just wrote down. But the smallest chest measurement, so that's going to be the people down at this end. And if we kind of start thinking about our numbers here, let's go back to this empirical rule real quick. So remember how we said this was 95%? Well, if 95% of the data is between here and here, and this is symmetric, that remaining 5% is split up on each end. So that means that the part that's on this side is 2.5%, and the part that's on this side is 2.5%. So your bottom 2.5% would be anybody below 2 standard deviations from the mean. So in our case, that would be anybody under 36 inches. So we would say under 36 inches. And so they're going to ask various percentages today, and you have to be able to look at this empirical rule and figure out where would that percentage fall? How can I arrange this and look at the numbers and think about it to get that to happen? So there's all the numbers we have on here, but then also, remember that half the data is on one side and half the data is on the other. So you can use that as a kind of a midpoint to help you figure some things out too. Okay. So that was one example with, some Scottish dudes chest measurements. There's another one on this page about SAT scores, which is kind of cool. So it says, recent SAT scores for college-bound seniors are normally distributed. That's our telling us, hey, we can use our empirical rule. The mean is 508 and standard deviation 121. Cool. How does the empirical rule help you understand performance of individual students? So what proportion of students are between these two scores? So again, you might look at that and go, that seems like some really random scores. But if we go ahead and make a little quick sketch of our normal distribution, middle number, 508. Sorry, it's not an 8. That's an 8. And then it's going to go up and down by 121. So if you take 508, add 121 to it, it's 629. So 1 standard deviation out, 629. And usually I'll go ahead and I'll just do all 3 of these. So I'll go out 3 different standard deviations here. So what do we have there? 750 and 871 would be our other increments. So I like to go 3 standard deviations each way, just when I'm sketching this out. I don't always need it, but it's just kind of helpful. And then if I subtract the standard deviation, I can do it 3 times here and get those 3 values. So what do we got? 387, 266, and 145. So 387, 266, and 145. So we use a standard deviation to sort of draw this number line that we can now work with. And so now we can look at this and we can answer this question usually pretty easily at this point. So when they say 387 to 629, that's 1 standard deviation in each direction. That is 68%. Okay, the first part of that empirical rule. So how would I answer it? I'd say there is 68% of students within that score range. Okay. And then the next one here says, what proportion of students receive scores greater than 387? So 387 and up. Here's how I would do this. Well, past 508, that's 50%. Okay, so that's 50% plus whatever this section right here is, which if you remember earlier, we labeled it on there, that's 34%. So 50% plus 34% is 84%. So you got to do a little bit of kind of reasoning here to sort of figure out, all right, how am I going to determine exactly what that percentage is? So you got to use some little tricks. The numbers that we have on our empirical rule are really helpful, but then also remembering things like just like, hey, half of the data is 50%. So everything to the right of the mean is 50%, left of the mean is 50% of the population as well. Now, you could ask all kinds of weird combinations here. I know it's not on here, but what if they said, what percent is between 266 and 871? Okay, what if that was the question? What percent of people fall within this score range? So you'd be like, well, okay, it's this. So starting at 266 to 871. So that's going to be from 2 standard deviations out in this direction to 3 standard deviations in this direction. So if I was doing that, I would use the fact that from 2 standard deviations to 2 standard deviations is 95%. And then remember, we said this was 2.35. I would then just add those values. So I'd be like, okay, it's going to be 95% plus the 2.35%. And so altogether, that'd be 97.35%. And so given any random, they're not going to be random, but any given range, you can then calculate the percentage as long as it's giving you ones that are within standard deviations. And that's all we're going to see today. Tomorrow, we'll look into what if they ask us something that wasn't directly one of these intervals? What if they said, who scores between 300 and 600? Because like 300 is going to be, here-ish, and 600 is going to be here-ish, and those aren't exactly on our lines. There's ways to do that too. We're just not doing that till tomorrow. So we're going to look at strictly within 1, 2, and 3 standard deviations away for today.